Hello, welcome to Notes for Verifying Identities. In the previous section, we went over the fundamental identities, which are the building blocks of what you have to know in order to go on. So as you notice at this, if you turn to the next page, you notice I put the three main identities up at the top here, the three Pythagorean identities, and I suggest that you always keep them by your side, ready to use whenever you need to, and derive them yourself so that you can do them by memory. Make sure, if you notice the notes here, make sure that we are only using substitution. It's the only property that you can use, is to substitute something for what it equals. You may not use any of the rules of equality. You're going to want to, you feel like you want to, because we're used to adding the same thing both sides, subtracting the same things both sides, but that is forbidden. You can't do that because you have not proved they're equal, so you can't use the rules of equality. So all we're going to do is substitute, and what I've shown you here, there are three examples, one for each of the Pythagorean identities, and you can see that I've needed to adapt them and use the different formulas we talked about in the first lesson. So if you're looking at part A, it says cosine squared minus sine squared. We don't have anything to substitute for that. You'll actually get a formula that is that later on, but we don't have anything yet. So we have to use a form of the Pythagorean identity so we can get the left side into all cosines, which is what the right side is. Keep this in mind. You're going to use that strategy later when we solve equations. We're going to want to get it all into cosines or all into sines. So we're going to take out this sine squared theta, and we're going to substitute what it equals. And I already wrote the change here, or if you can do it in your head, the sine squared equals, I wrote the cosine squared theta minus 1 minus cosine squared theta. Actually, we're going to use theta because that's what, you shouldn't mix thetas and x's. I used x's for the formula, but okay. And notice we're only working on the left side. People have different ways of organizing, but I usually put the equals on the left side, and we keep saying what it equals until we get to the right. So now we're just going to use rules of algebra. We bring down the cosine squared theta, and we distribute the negative, so it's negative 1 plus cosine squared theta. And now it's just simple math here. We have a cosine squared theta and a cosine squared theta, so we're going to combine those, and that will equal 2 cosine squares of theta minus 1. And we are done. Now you can just say, hooray, we're done, or you can just make your victory symbol here, whatever you want to do to show that you're done. The next one illustrates that you will not always have an x or a theta. You sometimes have a 2x, you could have a 3x. It doesn't matter what it is as long as all the angles are the same. So you could use your formula, and you don't have to write this in, but I'm going to show you. Instead of tan squared 2x plus 1, instead of the x, you're going to have a 2x. So I adapted the formula here. I got the tan squared by itself because in this problem we have secant squared of 2x minus 1, and we want to get rid of that and put in a tangent squared. So that's what we're going to do. We're going to put in tangent squared of 2x. And now, remember, we'll just keep carrying along a 2x instead of a theta. It's just, as long as the angles are the same, it's okay. But we're going to use, you might just at this point just say, okay, the cotangent squared times the tangent squared is going to be 1 because they're reciprocals, and when you multiply reciprocals, they're 1. But I will actually show it With the substitution, the cotangent squared is 1 over the tan squared of 2x. And then times the tan squared of 2x. Remember, a whole number goes into the numerator, so that means you now have 1. Okay? All right, then the next one, you actually notice that you have a cosecant squared x minus 1. So as soon as you see a squared of one of the trig functions and a 1, check out. Maybe you can use the Pythagorean identities. Sure enough, you can, because if you isolate the cotangent squared of x, you get cosecant squared x minus 1. So we're just going to put the cotangent squared x in there. And you will notice that this is the reverse of the reciprocal formula. We had said you could do them all in either order. So 1 over the tangent is cotangent, and 1 over the cotangent is tangent. So I could just substitute and write the answer. However, I'm going to show you, to prove it's true, that I'm going to show you, let's do blue, that 1 over tangent squared x. Remember, it always has to be squared. You can't interchange tangent and tangent squared. And that would be 1, the numerator, times the reciprocal of the denominator. I'm reviewing this because you are going to be using this very soon in your work. You're going to be using this rule that you multiply by the reciprocal of the denominator. And now we're done. Okay? All right, so next, the Pythagorean identities. Now we're going to go through another one. Anytime you see a negative angle, you have to remember your even-odd identities. You don't have to know the names of them, but you have to know what they equal. So here we have, the left side has negative angles. We need to get rid of that. So we'll go to and we'll write our equals. And we know the sign of negative theta is negative the sine of theta. So we're going to write that down. And in the bottom, the negative disappears, so it's going to be cosine of theta. Pardon my scribbly writing. Now, we're going to use a technique which we actually mentioned later on. When you have two terms in the numerator, but one term in the denominator, you could actually separate them into two fractions. And why am I thinking to do that? Because on the other side you have a separation of a subtraction, one thing minus another. So we need to split this into two things, and we'll have 1 over cosine of theta minus sine over cosine, and that should immediately alert you. This is why you need to have them by memory, and why we require memory for the very first test, is because it's when you have them in your head, you will recognize things immediately that they equal each other. So 1 over cosine is secant theta. Makes your job much easier if you use your memory, your brain. Okay, and then we're done. That was easy. Puzzle. Okay, now we have to get back to using our factoring skills that we learned the first semester, and one of them is greatest common factor. And why am I choosing that? Always think about why you're doing these things. Well, it's something that you notice can be done. We have a product here plus a product. Secant times secant is a product. So if you have a common factor, you can we sometimes call it reverse distribution. You can factor it out, and the greatest common factor is secant squared x, and that comes out in front. So we have secant squared x. We divide the GCF out of the first product there, and we get just tangent squared x. When we divide secant squared out of secant squared, we get 1. Then we notice, remember, you have your Pythagorean identities right by your side at all times. And if you notice, this actually is one of the Pythagorean identities. We don't even have to change it. So, excuse me, I should put my equals here every line. So we have secant squared x, bring that down, and this equals another secant squared x. And squared times squared is to the fourth power. Notice how much easier it is since we use this shortcut of putting the squared sign next to the SEC so that you don't have to be writing parentheses constantly. It's a very nice shortcut. Okay, next. Right, now another skill that we have is factoring a difference of squares. Now this one is in a squared minus b squared, but that just reminds you of the formula. This one is a fourth minus a fourth, and we've had this before. That's why we do our factoring unit right in the beginning of the year. We know that the fourth powers will break down into squareds minus squared and squared plus squared. So we're going to factor the top into sine squared. It doesn't matter if you do the plus or the minus first, but I hope you're thinking as you write this. I hope you're thinking, I know what that is, because I memorized that Pythagorean identity. Sorry, my sloppy writing, just bear with it. Sine squared plus cosine squared times sine squared minus cosine squared. And that's because if you look at the formula we're following up right above it, that's because a sine squared times a sine squared equals sine to the fourth. So we're doing it at a higher level than the formula is. And then the bottom is still sine squared theta minus cosine squared theta. And because we have a whole factor, now it isn't in parentheses, but it's nice to have it in parentheses if you're going to cancel it out. This whole factor of the whole denominator cancels out with the numerator, and we end up with, and I'm going to write a step here. I'm not going to skip any steps, but I'm hoping you're seeing something while I'm writing it. We know what that equals. Equals 1. There we go, and we are done. Always look out for that, and you'll find that that's one thing that, for your long-term memory. When you get to calculus, you want to automatically, anytime you see sine squared plus cosine squared, it equals 1. And you'll make your life much easier, like 100 times use a 1 instead of the 2 squareds. Now here's multiply, and I can tell you what, every year there's lots of students that don't multiply this correctly. So we start drumming it in Algebra 2, and I'm sure you've had it drummed in all this year. When you have a parenthesis squared, you have to, sometimes we say foil it, or you have to multiply it out. So if you have something to multiply out, you got to get rid of those parentheses, and that's the first thing you're going to do. You're going to say, how do I know what to do? Well, if there's something obvious like a GCF, do it. If there's something that looks like higher powers, then you know you have to factor it. If it's something that is a parentheses, then do it. And if you don't do it the correct way, which is what I'm showing you right now, if you don't do this the correct way, you will not get the right answer, and you will waste a lot of time getting the wrong answer, and you'll wonder what's wrong, but it won't work because you didn't multiply out. See what's happening here. We have our, I'm going to go by first, outer, inner, last. If you just go by, just make sure you get all 4. It doesn't really matter what order. But sine times sine, I better make little marks here. I'll make little dots. Sine times sine is sine squared. And then you go and get your sine times the cosine is minus sine x cosine x. And then, of course, you have your inner cosine times sine, another minus. Now, get in the habit, when you have a product of two things, make them match right away. I'm not going to write cosine x sine x because I just wrote a sine x cosine x. So you make your life easier if you just write them in the correct, the matching order right away. And then you go back and you have cosine times cosine is, remember, negative times negative is a positive. Okay, now I'll go back to my blue. Now hopefully you're seeing something right away here, but these are like terms and you wouldn't notice it as much if you left it as cosine sine. So, but we have a minus 2 sine x cosine x, and hopefully you're seeing right away that you have a sine x plus a cosine x, so you have plus 1. Now, I wrote it as it came, but if you saw the sine x squared plus cosine squared first, then you would have it in the right order. So I'm just going to fix it. This is really the same, but I'm going to fix it. Our positive 1 will come first. Our negative becomes a minus. And there we have it. We are done. There we go. Okay. Okay, rewrite. Okay, sometimes you don't know, don't have any idea what to do because you're not using, there's no squareds, there's no ones. So your last ditch strategy, when nothing else is appearing to you, is to rewrite everything in terms of sines and cosines. Now we can, we're just going to work with the left. Sometimes when I see something like that on the right, I just think to myself, okay, that is 1 over sine of x. Kind of tells you where you're headed, just to remind yourself. Okay, so, but let's take the left side. It's secant is 1 over cosine x. And then cotangent is cosine. Now this should come just as quickly to you as it is for me right now, because you have them in your head. That's why it's so important to learn them. Makes your life fast and easy, or easier and faster. Okay, 1 over sine x. Oops. And that, of course, equals cosecant x. So there you have it. Okay, last one for today is this technique of separating a single term quotient into two terms. And of course you have to know what term means, and you have to know what quotient means. Everybody knows what separate means. We're talking about a single term quotient. That means the denominator is one term. You may not split up either a sum or a difference, a subtraction or an addition in the denominator. So we'll take this one term, which is cosine theta, and we see an addition on the right side, so we know we have to have two different terms. So we're just going to split it up into 1 over cosine theta plus sine over cosine. And then we have exactly what we want. 1 over cosine is secant theta, and sine over cosine is tangent theta, and we are done. Okay, have fun with it, and we'll get some more complicated ones in the next lesson.